Let's start by using the prioritized differential diagnosis to interpret diagnostic tests. And we're going to launch into the section of Module 4 where we talk about how diagnostic tests help us. It's important to understand that uncertainty is everywhere in medicine. And we always have to proceed and work with uncertainty because there are very few tests that allow us to be 100% confident in our decisions. But we can get pretty close enough to act, depending on what our next step is for a given patient. And each test you do to evaluate a patient's complaints, including the first test, which is the history and physical that you take, will change your level of certainty about possible diagnoses. Remember, Mrs. Triglione asked, do I have a muscle strain that's causing my chest pain? And then you took a history and based on that test said, no, a muscle strain is unlikely. So even something as straightforward as a history and physical can change your level of certainty about a possible diagnosis. Effective clinicians, really expert clinicians, know how to use tests to impact certainty and diagnosis in the right way, whether they want to rule in a disease or whether they want to exclude a disease. So lots of times when you are on rounds in the hospital as a medical student or resident or in the clinic, your attending might ask a question like this. What's a good test for us to order for this particular patient in whom we're considering a particular diagnosis? And these are always a trick question. And the answer should be, it depends, right? So don't fall into the trap of just blurting out a test. You have to ask a clarifying question, and that will show you understand how important it is to know what you're trying to do with your diagnostic test. So it depends on whether it's more important that we are certain the patient has the disease. So we want to make absolutely certain our patient has a disease if we plan to start a risky or expensive treatment, right? So if the treatment, for instance, is chemotherapy for leukemia, we better be as close to 100% as possible that the person actually has leukemia before we start that treatment. Or is it more important that we're certain that the person is free of disease? And that would be the case if we want to reassure them that they are really healthy, or if we want to make sure that we're no longer considering a distracting disease and we want to turn our attention to considering a different disease. And by the end of this module, hopefully you'll be able to identify the circumstances and the right type of questions for, right type of tests to answer each of these questions. So what we're going to do today is first work through some statistics and some math to prove the points that we're trying to emphasize. Now, as I said earlier, those of you who like numbers and want to work along with your computer, feel free to do so. But those of you who don't like this so much, I'll be showing you plenty of examples and you can just work along with me. Don't panic. We'll make it as easy as possible for you. Then after we prove our points, we're going to show you some heuristics and tools, and a heuristic is just a rule of thumb, that will help you guide decision making on a daily basis without requiring you to walk around with a computer or calculator. If you want to use those are fine, but we'll give you some options to doing the mathematical calculations every time you order a diagnostic test. And then finally, we're going to apply the math and the heuristics to our existing knowledge base about how likely a particular disease is based on our prioritized differential diagnoses. A couple references for those of you who are interested. The first is an article written by myself and Mitch Meadow in Evidence-Based Medicine in December 2011. The heuristics come from this. You're welcome to read it. You won't need to in order to do the work. And then there's another wonderful general reference, Current Medical Diagnosis and Treatment, the text we recommended at the beginning. Chapter E3 talks a lot about the information we're about to cover, and so those of you with other questions might want to reference one of these two papers. So let's talk about performance of tests and general principles about performance of tests. So tests can be described or differentiated by the extent to which they distinguish between patients who have a disease and patients without the disease. That's why we order the test. And there are two characteristics of the test themselves that are very relevant to this work. The first is the sensitivity of a test. And the sensitivity of the test describes the proportion of people who have a disease in question who also test positive for that disease. So the proportion of all people with disease who also test positive for the disease or have an abnormal test result. The specificity of a test describes the proportion of people who are free from the disease who also test negative for that disease or have a normal test result. So these are inherent characteristics of the test before the test is given to your patient in question, and it refers to the performance of the test in general populations. Now, they're determined because the test has been tried on ideal general populations. And ideal in this situation, when you're defining test characteristics like sensitivity and specificity, means a population that has a mixed possibility of having that particular disease. In general, sensitivity and specificity are independent of the pretest probability or prevalence of disease. There are some exceptions to this. If the test has been tested in a population that has a very high pretest probability of disease, it might perform a little bit differently in a population that's got a more mixed probability. But this is sort of evidence-based medicine 201, and we're still on evidence-based medicine 101. As I mentioned, they're characteristics of the test themselves, not of the patient who has taken the test. And in generally, sensitivity and specificity are reciprocal. A test that's got a higher sensitivity generally has a lower specificity. And so the test you choose for a given situation should be based on whether you're looking for and prioritize sensitivity or looking for and prioritize specificity. The next several slides are going to work through the sensitivity and specificity statistics using 2x2 contingency tables, because they'll help us illustrate our point that interpretation of diagnostic test results requires that you understand how sensitivity and specificity impact your pretest probability of disease devised from your patient illness script. So those of you who are familiar with this concept of contingency tables may want to skip forward a few slides, but for those of you who are novices, I'm going to spend a little bit of time orienting you to the table and then how the statistics are calculated using this table. So first, let me orient you to the table. The columns represent disease state. This column here represents the population of patients in whom the disease is present. So if you had 1,000 people, what number of people would have the disease in question? And that's A plus C. The people in box A and the people in box C all have the disease. On the other side, this column represents the people in whom the disease is absent. And that represents the sum total of people in quadrant B and quadrant D. So B plus D are the people in whom disease is absent. Some people call this the healthy population, but it's not technically quite right because they could be free of this disease, but not free of all diseases. The rows indicate the test results in question. And when we get a test result back, we call it either positive or negative. Some people would call this a positive test as an abnormal test, and some people would call it a normal test. Quadrant A represents those people who both have the disease. We know this from the population in which the test was developed, and test positive for the disease. That's known as the true positive quadrant. Quadrant B here represents people who are free of disease but test positive for disease. So that's a mistake in the test, right? And that's the false positive quadrant. Quadrant C represents the people who have the disease is present, but test negative for the disease using this test. And that's the false negative, right? That's another diagnostic mistake from the test's perspective. And quadrant D represents those people in whom the disease is absent and who test negative for disease. So that's a true negative. So as we're considering diagnostic tests, obviously we want those tests that will have a greater proportion of true positives than false positives and a greater proportion of true negatives than false negatives. So sensitivity, let's look at the math, is the proportion of people we said who have the disease, so it's going to be in this column, who also test positive for the disease. And the mathematical formula for that is A plus C, that's the people in whom disease is present, as the denominator, and the numerator is quadrant A. Now, there's a shorthand we use for sensitivity to remind you of what it's good at doing, and that is SNOUT, S-N-O-U-T. And that stands for, as an acronym, a sensitive test, when negative, helps us rule out a disease. And this kind of makes intuitive sense when you consider that a sensitive test, a highly sensitive test, say it's 99% sensitive, means that virtually everyone who tests positive for the disease sits in this quadrant A, that there's very few people who actually have the disease who test negatively for the disease. So almost everyone with the disease is going to test positive. So if the test is negative, it means that this particular disease has been ruled out. So let's look at specificity. And here's the 2x2 contingency table for specificity. Now, specificity, remember, is the proportion of people who are free of disease. So that's the free of disease population is B plus D, who actually test negative for disease. And that's quadrant D. That's the true negative rate. And a specific test is therefore very good at ruling in disease, because a very specific test means that virtually everyone is free of disease tests negative for disease. So if that test turns up to be positive, the person probably has disease. And we can remember this with the acronym SPIN. Specific tests, when positive, rule in the disease. This is an important concept, and it bears taking a quick quiz to make sure we're all on the same page. When talking about a sensitive test, we're talking about a test that, number one, rules in disease when the test result is positive. Number two, is positive in people with the disease more often than it is negative in people with the disease. Or number three, is positive in people with the disease more than it is positive in people without the disease. These are tough questions. And the answer is number two. And let me remind you with our 2x2 table. Remember quadrants A, B, C, D. This is people with the disease. This is people without the disease. This is people with the positive test. And this is people without the positive test. And sensitivity is A over A plus C, the proportion of people with the disease who test positive for the disease. And so a very sensitive test has more test results in A than in C. For 3 to be true, we'd have to be talking about a different statistic, because sensitivity doesn't at all reflect performance of the test in people without the disease. That would be this column over here, and notice there's no B's or D's in this formula. So sensitivity and specificity are really important in helping us arrive at what we need to know, but they don't answer the clinical question that's always on top of people's mind, which is what happens to our clinical pretest probability as a result of the test? If the test is positive, how much more confidence do we have in our clinical diagnosis? And if the test is negative, how far does it fall down on our list of differential diagnoses? That requires that we take those test characteristics of sensitivity and specificity and combine them with our tiered pretest probability to arrive at that answer. To get at the answer of what a positive test means in my patient, we need to use the statistic positive predictive value. Positive predictive value answers the question, what proportion of patients with a positive test result actually have the disease? So positive test result, all of them who have a positive test result is A plus B, remember? That's here. All patients who test positive is A plus B. And what proportion of those actually have the disease is A, disease present and test positive, over A plus B. So that's the positive predictive value, and that's going to be the most useful information to us as we begin to test patients and compare it to our clinical pretest probability. Now, how do we get at that? Well, interestingly, in order to get at that, we have to fill in numbers on all of these quadrants. In order to fill them in accurately, we need to know what the prevalence of the disease in our test population is to get started. So we've added a row here. You see E and F as new letters, and E plus F equals all patients who were tested, whether they tested positively or negatively. So E represents all people who have disease in this population, whether they test positive or negative, and F represents all people who are free of disease in this population, whether they test positively or negatively. Now, how we get to E and F is we take all patients who are tested, say there's 1,000 of them, and we use our pretest probability, say it's 20%, and then fill in these squares. So if the pretest probability of disease is 20%, that means 20% of this 1,000 people will actually have disease, and that would be 200. And we're going to need that in order to get to our post-test probability and positive predictive value. So let's look and see how we might use this as we go forward. Again, what positive predictive value tells us is, given a positive test result in my patient, how certain am I that the patient has the disease? Negative predictive value is the converse of this. It's the proportion of people who test negative for the disease who truly don't have the disease. And again, we needed to add our pretest probability and our population of all patients who are tested, and we'll show you how to complete these tables in a couple of slides. But what we're interested in right now is all of the patients who test negative for the disease, which is C plus D, as the denominator, and the numerator would be then D, the numerator of interest, which is D over D plus C, the negative predictive value. Another way of saying that is, given a negative test result in my patient, how certain am I that the patient is free of the disease in question? Now, I want to point out something really important here. The negative predictive value tells you how likely it is your patient doesn't have the disease. It doesn't tell you how likely it is that your patient has the disease with a negative test. It doesn't describe the false negative values that we referred to a couple slides ago. So what if you want to know about that misdiagnosis? What if you want to know what proportion of people who have a negative test actually still have the disease? That's the false negative rate. And mathematically, that is equal to 1 minus the negative predictive value. The other misdiagnosis you might get from a test is a false positive test. And that would answer the question of what proportion of people with a positive test result are actually healthy. So they're falsely accused of having the disease, whereas these people are falsely assured that they're healthy. So let's take a couple quizzes to see if you've understood what we've just been talking about positive and negative predictive value. First quiz, Dr. Osler is somewhat concerned that his patient might have a terrible disease. He orders a test, and the result on that test is positive. The statistic that describes the proportion of people with a positive test result that actually have the disease is known as sensitivity. Number 2, specificity. Number 3, positive predictive value. Number 4, negative predictive value. Or number 5, 1 minus the negative predictive value. And to answer that question, let me remind you of our 2x2 tables. This is disease, positive and negative. This is test, positive and negative. This is all who test positive and all who test negative. And we remembered our conventions A, B, C, D, right? So what we're asking, what Dr. Osler is asking is, what's the statistic that describes the proportion of people with a positive test, all of these people have a positive test, who actually have the disease, and that would be here. So it's A over A plus B, which is the formula for positive predictive value. Got it? Great. Now, I'll tell you that when you face questions like this on tests in the future, it's always helpful to kind of sketch out this 2x2 table and try and figure out what it is they're asking for within this table. That helps many people get the answer right. So the answer here is positive predictive value, the proportion of people with a positive test that actually have the disease. Quiz 4.4. All right, so Dr. Osler's colleague, Dr. Halstead, is our quiz 4.4, so it gives you another opportunity to work through one of these contingency tables in the abstract. So Dr. Halstead is somewhat concerned that his patient may have a terrible disease. He orders a test result, and that test result is negative. The statistic that describes the proportion of people with a negative test who still actually have the disease is number 1, sensitivity, number 2, specificity, number 3, positive predictive value, number 4, negative predictive value, or number 5, 1 minus negative predictive value. Choose your answer, and then we'll draw a table to analyze this question. Okay, so let's draw our contingency table really quickly here. Remember, disease, positive or negative, and this is test, positive or negative. Our convention is this is A, B, C, and D. All who test positive are in this summative quadrant. That's A plus B. That's all who test positive. All who test negative are in C plus D. Those are all who test negative. And what Dr. Halstead is asking us is that in a population who tests negative, so that's all C plus D is our denominator, what's the possibility that the person still has the disease? So here's our disease column, and C is the person who still has a disease, who tests negative for a disease. So Dr. Halstead is asking us for the statistic that is represented by the formula C over C plus D. And that is 1 minus the negative predictive value, or the false negative rate. Oftentimes, people mistake that for the negative predictive value. Negative predictive value, remember, is D over C plus D. And that refers to the proportion of people who test negative for the disease who actually don't have the disease, who are healthy. It's the true negative test. And what Dr. Halstead's asking for is the false negative. Got it? Okay.